Hi, my name is Mariana Lume. I'm a geophysical engineer and second-year Master of Science student at the University of Calgary under the supervision of Dr. Chris Einanen. And today I will present a study entitled Local Optimization Approaches for Simultaneous AVO Inversion based on re-parameterized Zoeppritz equations. Conventional approaches to invert pre-stack seismic data involve linearized approximations of the Zoeppritz equations. One successful method is the weighted stacking technique, first proposed by Smith and Whitlow and expanded by Stewart and Larsen, which consists in the minimization of the L2 norm between the observed data and its theoretical description using the Aken-Richards approximations. Then a resulting pair of equations will allow us to compute the fractional, compressional, and shear impedances encompassing the multiplication of the PP and PS reflectivities and its time and angle variant weights. This technique produces very accurate estimates as long as its underlying assumptions are met. That is, if we can guarantee weak contrast of the elastic parameters between the interface, incidence angles smaller than 35 degrees and smaller than the critical angle, and values of the VPBS ratio between 1.5 and 2. The traditional procedure when the incidence angles are higher than the critical one is to limit them, but this compromises the reliability of the estimates since in some cases this critical angle may be as low as 25 degrees. Additionally, there is a growing interest in seismic acquisitions of long offset ranges for different industry purposes. For instance, when we want to study reservoirs that exhibit a strong contrast in their interface, for example, when they contain heavy oil accumulations or when we are dealing with basalts and or salt domes. Therefore, since linearized inversions would not allow us to compute accurate estimates if the incidence angles are higher than 35-40 degrees, we develop an inversion strategy appropriate for long offset acquisitions and hence large incidence angles. To achieve this, plane wave Zoeppritz equations were considered because these are not conditioned to any particular range of angles. However, we would be doing a plane wave approximation because real seismic data is produced by a spherical wave and not plane wave. Here, alpha, beta, and rho are the P wave velocity, S wave velocity, and density, while I and J are the compressional and shear impedances. The Zoeppritz equations were re-parameterized in terms of the upper medium properties that are these variables with the subscript 1 and in terms of the jumps of the elastic parameters, which is familiar from AVO analysis. To accomplish this, terms A, C, and D were modified using this expression that is commonly applied when linearizing problems. And now, each element of the matrix P is a nonlinear function of the fractional compressional and shear impedance and the fractional density. We can use this information to compute an additional parameter that is this fractional VPBS ratio that will give us more information within the reservoir in terms of changes of the lithologies and fluid content. To work with PP and PS data simultaneously, different incidence angles were obtained for both PP and PS modes of energy conversion, in order both plane waves reach the same receiver after reflecting in their interface. This means that the forward problem needs to be computed twice, once with the PP incidence angles and another time with the PS incidence angles. And then we will use this information to construct the appropriate vector of coefficients. And we will extend this analysis when performing the inversion. On the other hand, we introduce a sampling operator S that will allow us to extract only the PP and PS reflectivities when it's necessary. Now, to invert the reflection coefficients, we can perform an unconstrained optimization, minimizing the L2 norm between the observed data and the predicted data. Here, W is a diagonal matrix that contains the standard deviation of each data set. And this term is the inverse of the data covariance matrix, where its elements act as weighting factors. After deriving the objective function respect the model parameters, we will obtain the expression of the gradient, that is this one over here, where J is the Jacobian matrix, calculated with this formula that contains the derivative of the predicted data respect the model parameters. Then the main new task is to compute the 48 elements of this term over here. To start the iterative process in a local optimization algorithm, we need to supply a reasonable starting point. And we can use the local gradient and or the local curvature, that is the Hessian, to compute updates of the model parameters per iteration using this expression over here, where the matrix B is adapted to the following matrices depending on the optimization algorithm that we decide to apply. In the case of this study, we work with steepest descent, Gauss-Newton, and the Levenberg-Marquardt modification. To test the developed formulas, we work with a two-layer model of solid units in welded contact, with a range of offset from 0 to 4,000 meters, and with intervals of 80 meters between receivers. The ray tracing was performed to obtain the incidence angles for the PP and PS datasets. Here in this figure, we can observe the true model represented with the continuous lines. And this was designed with elastic parameters that allow us to meet most of the underlying assumptions of the weighted stacked inversion. However, if we recall, this linear technique is only well suited when the incidence angles are smaller than 35 degrees. But after performing the forward problem, we can see in this figure that almost half of the incidence angles are higher than this value, reaching a maximum of 53 degrees for the PP dataset and 65 degrees for the PS dataset. Additionally, in this figure, we can also see the initial model represented with dashed lines. And this was constructed from weak perturbations respect the true values of alpha, beta, and rho. However, since the impedances result from multiplying velocities and densities, the initial value of the model parameters that we would be inverting were not that small. When inverting broadband and noise-free reflectivities, we can observe in the figure above that all the optimization methods reach convergence at a different iteration number. For example, pure Gauss-Newton was the fastest method, finding the minimum point at the second iteration. However, steepest descent and Levenberg-Marquardt had a slower performance, finding the invariable values at the 17 and 10 iterations respectively. We can also observe that after reaching convergence, all the estimates were very close to the true values of the model parameters, represented with the dashed lines. And in the figure below, we observe that after reaching convergence, all the data residuals were almost zero for all the optimization methods. In particular, the RMS error in the steepest descent methods for the PP dataset had increasing values at early iterations, indicating that this method is somewhat more unstable than the other two. In this figure, we can see the comparison of the results obtained with the linear and the nonlinear inversion. We can observe that all the nonlinear algorithms got trapped into the same local minimum. Additionally, the estimation of the fractional compressional impedance, the fractional shear impedance, and the fractional BPBS ratio was more accurately done than the estimation of the fractional density made by the optimization algorithm. And in general, the nonlinear inversion had a better performance than the weighted stacking technique, exhibiting differences of approximately 2.5% between both approaches. To invert broadband and noisy reflectivities, identical and independently distributed noise was generated from a Gaussian distribution about zero and with a standard deviation that was calculated with the RMS power of the reflection coefficient and an indicated signal to noise ratio. The nonlinear inversion was performed with and without including the inverse of the data covariance matrix. And both the linear technique and the nonlinear inversion were performed 5,000 times in order to analyze the results statistically while comparing the maximum likelihood solutions. In these figures, we can observe the results and the resemblance of them with respect to the obtained after inverting the broadband and noise-free reflectivities, which means that again, the fractional density has the highest percent error and all the optimization algorithms got trapped into the same minimum point. On the other hand, even though the linearized inversion helps to suppress noise due to the nature of the stacking procedure, in general, the nonlinear inversion had a better performance with or without including the inverse of the data covariance matrix. And after including noise information in the inversion process, the percent error of the fractional compressional impedance and the fractional density had a slightly increase, while the percent error of the fractional shear impedance and the fractional BPBS ratio had a subtle decrease, which indicates that including noise information during the inversion helps to do a better estimation of some model parameter, which is beneficial for reservoir characterization. Now, to invert the band limit and noisy reflectivities, the noise-free synthetic PPMPS datasets were filtered with an Orsby wavelet with the following frequency characteristics, and then were contaminated with IID noise with the same features described previously. In this figure, you can observe the synthetic seismograms obtained after convolving the noise-free PPMPS reflection coefficients with the Ormsby wavelets. Again, the inversion was done 5,000 times in order to analyze the results statistically and compare the maximum likelihood solutions. In this figure, we can observe the results obtained, and we can see that once more, the nonlinear inversion had a better performance than the weighted stacking technique. And all the optimization algorithms produce estimates that were almost identical. We can see that after including noise information during the inversion, there are some improvements in the estimation of the fractional shear impedance and the fractional BPBS ratio that this time are more notorious. And in particular, when inverting band limit data, the percent errors are higher than those obtained when inverting broadband data. But for most of the model parameters, the percent errors stay within an acceptable range. The exception was the density that showed an increase in its percent error, reaching around 67% when not considering the inverse of the data covariance matrix and 67% when considering it. This indicates that the PPMPS datasets have little sensitivity to this model parameter, not doing a proper constraint of its band-limited true value. To understand the effect of the initial model in the results, some experiments were done strongly perturbing only one initial model parameter and leaving the others with the original or the same magnitude in the original initial model. These tests were done with the pure Gauss-Newton method when inverting broadband and noise-free data, and the results were compared against this one that was obtained from the original initial model. We can see in this figure that if we only strongly perturb the initial p-wave velocity, all the percent errors increase with respect to the original one. But if we only strongly perturb the initial s-wave velocity, all the percent errors increase by 1.5 times the previous result. However, if we only strongly perturb the initial density, we can see no difference between both accuracy tests. This suggests that mainly the initial value of the p-wave velocity and the s-wave velocity are the ones that are going to affect the final estimates. And the stronger the perturbation of the initial value of the s-wave velocity respect its true value, the less accurate are going to be the results. A good initial model is necessary in order the outperformance of the nonlinear inversion could be guaranteed. In this case, we need to meet with some relationships between the initial alpha and beta perturbations. For example, in this figure, we can observe an initial model represented with dashed lines, and this was constructed with a ratio between the initial alpha and beta perturbations of 6:1, which is too large. Then, the estimation of the fractional shear impedance was more accurately done with the weighted stacking technique than with the pure Gauss-Newton method. But for different initial models, like these ones over here, where the ratio between the initial alpha and beta perturbation is 2:1, the percent error of all the model parameters were almost zero. Other acceptable ratios are 1.5:1 and 3:1. Finally, we can understand the benefits of incorporating the PS reflectivities to the nonlinear inversion process after comparing the joint PP and PS inversion results against the ones obtained with the conventional PP inversion. For example, we can see in these figures that we have the normalized histograms constructed from the estimates obtained after statistically inverting band limits and noisy reflectivities using the pure Gauss-Newton method. For example, in this case, we can see that even though the simultaneous inversion sacrificed a bit of accuracy in the estimation of the maximum likelihood solution of the fractional compressional impedance, the estimation of the fractional shear impedance and the fractional VPBS ratio was more accurately done with this technique than with the conventional PP inversion. Additionally, the estimation of all the model parameters was much more precise with this simultaneous inversion than with the conventional inversion, indicating that it is more likely, or there is more probability that this simultaneous inversion will produce better results. Unfortunately, in terms of the fractional density, both types of inversions could not produce very accurate maximum likelihood solutions for this parameter. But statistically, the simultaneous inversion was much more precise. On the other hand, when performing the conventional PP inversion, the condition number of the Hessian was approximately 300. And when performing the simultaneous inversion, the condition number of the Hessian was approximately 24. Hence, similar to the results shown by Larsen in his studies, incorporating the PS reflectivities to the inversion process helps to stabilize it. To conclude, synthetic data allow us to demonstrate the outperformance of the simultaneous nonlinear AVO inversion over the weighted stacking approach under scenarios of long offsets, but conditioned to a sufficiently good initial model. Regardless the optimization algorithm, convergence was reached to the same minimum point, but exhibiting different convergence features, being the pure Gauss-Newton the fastest method. On the other hand, including noisy information improved the estimation of the fractional shear impedance and the fractional VPBS ratio. And these enhancements were more notorious when the data sets were band limits, which is beneficial for reservoir analysis and reservoir characterization. And additionally, the benefits of incorporating the PS reflectivities during the nonlinear inversion were demonstrated through the high accuracy and precision of its results. And finally, there is a negative impact in the estimation of the fractional density, in particular when the data sets were band limits, because these PP and PS reflection coefficients have little sensitivity to this model parameter, not doing a proper constraint of its right value. We would like to thank the cruise sponsors, faculty, staff, and students, as well as the NSERC for their continued support. Here are some references used for the completion of this study, and thank you very much for your attention.